Okay, I'm Todd Brimmer. I'm from QLogic. I want to talk a little bit about our PSM tag matching API and some of the results and capabilities of that. So I want to really go through first off, what is PSM? How is it different from verbs? And then I'll talk a little bit about some of the advanced features that this has enabled us to develop and some of the results that we're seeing with the performance and scalability using this interface. So first off, what's really important to understand is, what is PSM? We've actually open sourced this as part of, came out the first time around in the OFED 1.5.2. It's in all the future versions of OFED. This is something that we designed very specifically targeted at HPC. We did this by looking at what the actual needs and requirements were for MPI and other evolving HPC requirements, and then designed the API to exactly meet those needs. This allowed a very good division of responsibility, looking very carefully at how the MPIs were architected, and let us retain in MPI, of course, all the complex functions and the wide API and the other support that MPI needs, and allowed us to focus very much on the interconnect specific details so that we could focus on what's the best way to really move data in an InfiniBand network, and then what advanced features are really applicable and necessary, such as dispersive routing, quality of service, adding the resiliency factors that are needed to deal with large clusters. All this was done as a user space library, so there's low overhead in terms of using it and excellent performance. Now, really to understand why we would even consider doing any of this, it's important to step back a little bit and look at the history of InfiniBand and where InfiniBand came from. So in the late 1999-2000 timeframe, the InfiniBand standard was conceived by the merging of the Future I/O and the Next I/O groups headed by Intel, IBM, Oracle, and others. At that point in time, what they were really looking at solving was a network I/O paradigm problem for the data center. There was a lot of focus on channel-type interfaces that were prevalent in mainframes and how could they build mainframe-like capabilities out of commodity hardware. A lot of focus on how can we replace Ethernet and fiber channel and just redo the entire data center infrastructure with those networks. And so as a result, a lot of what InfiniBand did is look at how fiber channel worked, how Ethernet worked, how IBM channel interface worked, how the PCI bus worked, and came up with a design focused around those kinds of requirements, thinking a lot in terms of 100 node clusters and maybe achieving 100,000 or 1 million IOPS per second for I/O environments. And that was really the focal point of designing verbs. Now, what's happened since then is in the mid-2000s, the whole movement to cluster computing and HPC started to occur as the various vector processors kind of ran out of gas, and Moore's Law wasn't really keeping up with the exponential 2x per year growth rate requirements of HPC, and that led us to where we're at today with cluster-based computing. We had the advantage of really kind of focusing our effort at that point in time, really starting a lot of the effort for our adapters and PSM type design around that. And so that was a very different set of requirements, focused very much on the bandwidth and latency, focused on very large cluster sizes, and requirements that were order of magnitudes larger in terms of messaging rate. So stepping back then, given those requirements, we decided that some of the key things to focus on were the real needs of the HPC and especially the compute side, which was predominantly MPI at that point in time. So we wanted to focus very much on messaging rate and scalable latency, keeping the memory footprint as small as possible, making sure that it was able to support a stateless design, avoid the needs for caches, keeping the memory usage very carefully planned so that we could grow the cluster sizes easily, making sure that there's a resiliency. So in HPC, there's a very different challenge from some of the I/O paradigms and some of what's actually built into InfiniBand. You need to be able to deal with congestion and retry mechanisms. You need to be persistent. If someone accidentally bumps a cable and reinserts it 10 seconds later, you don't want the job to die. You want it to keep running through that. So you need different strategies in terms of retry algorithms, back-off algorithms, and persistence persistence. And then you need to start overcoming some of the inherent weaknesses that came about from focusing on I/O. So how do you do dispersive routing of individual messages down different paths? How do you do out-of-order packet handling? How do you maintain the interoperability while providing these advanced features? And finally, allow a way to continue to develop more and more advanced features in a way that all the different MPIs and other evolving APIs can take advantage of them. So what the architecture ends up being is that PSM is a peer to verbs. It's you can still run all your verbs capabilities. You can take advantage of that for MPI. You can certainly that's an excellent interface for doing SRP and file systems and other things that have an inherent I/O paradigm. But then you can also have the use of PSM predominantly focused around the MPI and the other evolving API. So this gives you an excellent full suite of capabilities. So, because of this design point around, how have HPC interfaces and what are the real needs of MPI, it resulted in an approach that would have a very good impedance match with the actual needs of the MPIs. Looking at, for example, Open MPI, you'll see that there's, order of the magnitude of difference here in the size of the amount of code needed to support PSM versus supporting verbs. And the complexity of interfacing with PSM is on par with a lot of other historic HPC interfaces such as Quadrix, MirrorNet, and others. The relative sizes for the other MPIs and for the vendor-specific MPIs that come out are all about the same difference by about an order of magnitude. And this is because PSM was really designed to focus very closely on the exact needs of these APIs. Looking at something like MPI receive in the Open MPI implementation, there's really only 2 lines of code in there that are specific to PSM. The rest of it's the kind of the standard boilerplate for creating a receive channel for MPI in the MTL interface. The send is the same as well. There's really only a couple of lines of code to handle it. The rest of it's the kind of the standard boilerplate as part of an MTL interface. And this also allowed us then to push a lot of features down into the library and permits a careful choice as to which things will be supported in hardware versus software and future migration of some of these capabilities in between hardware and software as we discover new needs or fine-tune for newer speeds. So some of the things that are in the library itself is a lot of the sophisticated features that you may see elsewhere in other solutions, such as tag matching is actually done in the library and supported by the hardware. There's per message selection of the strategies that can be carefully tuned and the proper trade-off points for when you're going to do various types of RDMA type approaches versus message send type approaches can be carefully tuned to the different models of hardware as they come out. Multi-rail support for handling multiple adapters and multiple ports in the same server. Dispersive routing of the ability to send traffic over multiple interfaces, potentially even segmenting the same message to have different parts of it going over different interfaces so that the overall bandwidth available to an individual message can be increased. And then resiliency algorithms ranging from flow control approaches to retry approaches, persistence, and how to tolerate jitter, as well as the whole memory locking strategy. So by doing a lot of this approach inside the layer, we can make the decisions as to when we really need to lock memory and how to do that versus the cases where there's strategies that may not involve any memory locking at all, and we can reduce overhead and simplify the interface. Some other things that you can then do inside the interface that are implemented presently include GPU integration, support for the whole process of establishing endpoints, which, as we're all aware, can be a challenging process to implement and needs to be scalable. As part of this, we can have multiple strategies for path resolution. So on simple fabrics, we can do lit exchange, as is done in many of the other solutions, and assume that things like P keys and SL cells are going to be identical for every single path. But we can also then do more complex solutions involving interactions with quality of service and partitioning configurations, and even have an approach for scalable path record queries. So for complex fabrics like toruses or meshes, or when those get disrupted, you can handle the fact that some of the path records are going to be very different from others because they have to use completely different virtual lanes or maybe even different addresses and go through completely different routing strategies to handle disruptions or other complications. And then quality of service also becomes a capability that you can do either by specifying quality of service levels per job. You can even take advantage of multiple quality of service levels in a single job and actually have your bulk messages versus your control messages go on different quality of service levels. So, for example, while you're doing application level credit exchange and acknowledgments, you can have them on a very high priority quality of service level and ensure that you avoid head of line blocking type situations and allow their progress to occur, while putting the bulk messages on a different quality of service level, allowing those to compete with each other and to move along with a different degree of performance. You can also configure CPU affinity and add a whole bunch of additional statistics about debugging and gathering things that help you to debug your MPI implementation. And so by localizing all these features into the library itself and keeping them close to the interconnect, it allows them to be instantly available for all the MPIs, so that if new development comes out that adds a particular interesting feature or fine-tunes a way of moving data, it's available immediately to all the different MPIs that are taking advantage of the interface, and you have all the goodness of shared and common code. So just to make a little more concrete a few of these examples and what they really mean. One example is dispersive routing. And so in InfiniBand, you can define multiple routes through a fabric using LMC, assigning multiple lids per device, each of which gets a different route. And now you want to take advantage of those. So you can allow essentially a source-directed choice of route by letting the sender choose which of these destination addresses to use as part of its message transfer. And we can have strategies like, for example, our short control messages may all go over a single path. They often require a degree of ordering and delivery, so we can use those in one path. But then for long messages, we can actually send them over different paths. We can send a single message over multiple paths, reassemble it on the receiving end, and employ round-robin algorithms to take full advantage of the bandwidth that's available from those additional paths. It also helps a lot to reduce congestion and other conflicts and hotspots because it spreads out the load being just generated by a single node. And so now you can have better sharing of ISLs. You can reduce some of the potential for the congestion in the fabric, in the core of the fabric. So for one simple example, in a 64-node cluster, comparing a pure single-path type routing with a single address per node and all the traffic between any pair of nodes using a single path to dispersive routing, we see a significant jump. The sad fact is that when you're using traditional static routing mechanisms, it really isn't going to generate a perfect route. It's going to have a deterministic approach for creating the routes, but they don't always match well to the semi-random traffic patterns that the applications have, especially when you start to lay multiple applications down on the same fabric and they're all interacting with each other. So it's virtually impossible for a static routing approach to anticipate the real traffic patterns that will occur as different applications run and as they enter different phases of their computation with different traffic patterns. So dispersive routing helps to spread things out and give you an approach to improve the performance. Another opportunity is GPU optimization. Obviously, GPUs are a very hot and exciting topic in our industry today. So this allows you to rapidly ensure that GPU capabilities are available for all the MPIs by having this centralized approach. So one of the things that's going on in the GPU world is GPU direct, basically trying to eliminate some of the additional data transfers that have to happen as a result of moving data between the slave or the target device that's the GPU and the CPU that owns control of the adapters and the PCI buses associated with them. So by taking advantage of the centralization of software into PSM, we're able to run and demonstrate the GPU direct capabilities very easily for a wide variety of MPIs. In this particular example, using some of the Tesla GPUs, we're able to see a 44% performance improvement by turning on GPU direct in the PSM layer without involving any other changes to the MPI environment. And this gets you take full advantage of the compute capabilities when you're using GPUs. Another interesting example of capability we're able to centralize is path resolution. So for most of the fabrics out there today are typically fat trees or some version of an oversubscribed fat tree. And in those kind of fabrics, just exchanging the lids is a sufficient and simple solution. It gets everything up and running. You can also pass in parameters such as a P key or a service level for the entire job, and everybody will run that particular job will run on a given partition or a given service level. But when you get to more advanced fabrics, especially meshes and toruses, you need to really inquire for the full path records. You also need them if you want to start doing things like handling disruptions in a torus, where the typical door routing algorithms fall apart if you start to disrupt the fabric by turning off selected switches or losing entire banks of cables, in which case you want to be able to route around them, and you need alternate routing algorithms, and those routing algorithms will typically change the service level or the destination lid or both that you need to use, so that you will be able to not introduce credit loops, but will be able to have just the traffic that was impacted rerouted. You also oftentimes want to take advantage of virtual fabrics and quality of service and assign different jobs to different quality of service levels. So if you're running a capacity machine that may have 10 or 1,000 jobs running at once, you want to put them on different quality of service levels so that your high priority jobs can be running and get the best capabilities or priority of the fabric, and your lower priority jobs, perhaps researchers that don't quite have the same degree of funding or student research or things like that, can be assigned a lower quality of service level. And then you also have the potential that you may want to use fabrics as a quality service and virtual fabrics, as I mentioned, separate the control and the data within a single job to control how those are going to interact and make sure that your high priority small messages make it through the fabric quickly and avoid any potential congestion that may be occurring due to large messages that are occurring even in the same job. And so by implementing and centralizing all these capabilities, we can hide this complexity from the MPIs, make it available to all the MPIs at the same time, and provide simple parameters to enable and disable these capabilities. And then we can even do things like specify a unique service ID per job so that the path record queries will respond differently, referring to a different virtual fabric or different quality service level. And so by taking this approach, we can do a very scalable solution that takes the right approach for each environment. So this actually also then enables us to do a technology with a path record replica per node. What the interesting thing here is that this approach lets us synchronize this replica with the centralized subnet administrator and only need to update that replica as the fabric changes. So the subnet administrator can send out change notices, notify the replica that a particular node has appeared or disappeared, and as a result, the replica can synchronize just the subset of information it needs. This information can then persist on the node beyond the life of a single job. So when you start up a brand new job, the information is all immediately available on node and doesn't need to go to the centralized fabric manager to get the data. Using this approach, we can handle in the replica well over 1 million queries per second because the information is all localized, and we're merely answering the same set of questions for each of the ranks in the job. So it can scale very well to multi-core, many-core type environments without burdening the fabric. And this also allows you to, of course, then start up those jobs without making the essay a bottleneck for that job startup. So it gives you a very scalable approach to addressing the overall handling of path resolution. So one of the other things we focused a lot on was, collectives and the importance of scalability and overall performance in the fabric. And what we found in our studies were that really at the heart of collectives was achieving a high messaging rate and very scalable latency. And those were two of the design focuses early on in the API and in the implementation of it. So by doing this, we were able to get the native collectives within the various MPIs to all scale and perform very well without needing any specialized collective-oriented hardware acceleration for the present generation. So the result is you get the full availability of all the different collectives, all the different MPIs, all the assorted collective algorithms. There's a lot of researchers that have been writing different algorithms for collectives that work differently on different types of topologies that take advantage of different techniques. And so you have all of those available. So for example, in OpenMPI, there's quite a wealth of components that you can select from the component library for collectives. And they're all available. They're not interconnect specific as a result of this approach. So the result here is an example of some data from a 1,200 node Westmere system installed last year at Lawrence Livermore using the QLogic QDR equipment, the HCAs and the switches, using out-of-the-box OpenMPI with the PSM MTL that ships with OpenMPI and the PSM capabilities that are in OFED and the default collective algorithms. The net result here is the algorithm scaled very much to the exact shapes of the curves that we'd expect to see based on the approaches in those algorithms. A lot of these were double reduced type algorithms that should have a log 2 type growth pattern, and we're seeing those exact shapes in these curves. So we're seeing that the standard collective scale very well with this approach, and by focusing a lot on point-to-point latency and messaging rate, we're able to leverage that capability into the collective performance. This all then translates into application scalability. So collectives are a key part in the scalability of most applications. For example, in Fluent, that's one of the challenges in scalability is how collectives are used and making sure they perform well. By taking this approach, the results here are example with QDR as we moved from the west to the Nehalem, from Nehalem to Westmere. And the solutions actually scaled perfectly with both the core count increases, and then as we started to build larger clusters, the node count also continued to demonstrate a similar growth curve. So this really means that we're able to take full advantage of the CPUs and GPUs as they advance, and by having this kind of performance capability, the scalability is available to the cluster. So in short, the interesting thing here is that PSM is now completely included in OFED. It's completely open sourced. It's a very highly optimized API focused around the needs of MPI and HPC environments. It gives us a very precisely chosen abstraction layer to meet the needs of MPI, relieving all the interconnect details from the MPI implementers so they can focus on the future capabilities of MPI as they look forward to the MPI 3 standard coming out and some of the challenges and features they'll need to implement in MPI. It gives us very good scalability by focusing a lot on messaging rate and scalable latency, and the performance then translates into an excellent capability for collectives. And this ends up resulting in good application scalability and performance across all the MPIs, across a wide range of applications. All right, thank you. Sure. Yes.
Can this be used with random forward table?
With random forwarding table?
Yeah, random. So there's an option in the nobody implements it. So, well, in the spec, there's an option for IDA. There's just an option for random forwarding table. So instead of forwarding the lid to
Yeah, I'm not sure I really understand the question. The random forwarding table, the random forwarding capability in InfiniBand is defined as a different way of programming, lid to port mapping within switches. So, in the standard linear forwarding table, you program your lids sequentially, and they each point to a different port. The random forwarding table approach is something in switches where rather than a switch, say, having 1,000 sequential lids, it could have a very sparse matrix of lids and how they map to ports. So PSM certainly is completely independent from that capability. Any standard lid or address that's needed to address a remote node can be used.
So we're going to spread out the injection from the point in the fabric, right? Like when it all get there to be dealt with, it was going to inevitably arrive out of order.
Maybe I misunderstood the question. So the facility that we're using, for example, for dispersive routing is LMC, where you assign different multiple lids to a given node. And then each of those lids can be programmed into the switches with different routes, so that after you leave the node, they can go to completely different portions of the fat tree, go through different core switches, and then come back to the destination. So that gives you different paths through the core of the fabric. And then what we have the capability is to deal with out of order and reassemble those messages, because they will arrive out of order. Those different sections of the core fabric may have different degrees of congestion, may even have different degrees of performance available to them.
Go ahead, let's get more.
So PSM is EU OFED now, but it is still only working for QLogic hardware?
At this time, we've focused our implementation on fine-tuning it for our hardware implementation.
Yes.
But it's now completely open sourced.
On your comment. So the PSM is specific to QLogic, right? So when we developed our MPI to interface to PSM, we actually designed a independent tag matching layer called TMI, so that we wouldn't have a specific vendor's API directly in our MPI. So right now, since there's really only one interconnect that supports this within the Open Fabric community, it's probably not a need for a generic API, but if other interconnect vendors decided to build tag matching type of hardware, we could maybe provide that mid layer. It's very, very thin, but it allows multiple vendors interconnects to plug in that provide tag matching, and we implemented 2 different ones, Miranet and PSM through them.
Right. The important thing to realize is the upper level API here is not require any special capabilities of the hardware. It allows that all to be done in the...
But your infrastructure doesn't have the ability to plug in different kinds of, or different vendors' interconnects, correct? It's specifically for your device.
At this time, yes.
And what we did was just a very, very thin layer that the only thing it does is provide that registration and the ability to add different interconnects.
Yeah. Mm-hmm.
So the second question. So PSM is supporting multi-wheel, right? So does it work with the HA failover?
Does it work with?
HA failover.
So we do have, right now we have multi-rail capabilities. What we focused on were the capabilities of associating CPU affinity to different rails, so that as we get many core systems, we can have different groups of CPUs, each focused on a different rail. So right now we haven't done high A, HA type failure.
You support multi-wheel, right? If one wheel fail, does it break everything?
Not at this time.
Okay. All right. Thank you very much, Todd.